Using a Quill tube, we can find the atmospheric pressure, and it can also be used to verify the Boyle's law. The Quill tube is a glass tube with thin walls. Its length should be about 1 meter and its diameter should be about 2 millimeters, and also should contain mercury column that is about 10 centimeters in length. I will explain the preparation of the Quill tube later. So if you think about the materials and apparatus required for the experiment, obviously you need a Quill tube and a clamp stand to hold the Quill tube like this, and a meter ruler to get the length measurements. As you can see, the air is trapped inside the Quill tube by this mercury column. So what we are going to do is to get different values for the length of air column versus the inclination of the Quill tube. Then let's consider the list of variables required for the experiment. The simple h is the vertical height from the table to the top of the Quill tube. Then length, simple L, is the length of trapped air column. Simple X is the length of mercury column. And capital L is the length of the Quill tube. Additionally, we need these two data as well, that is the density of mercury, and capital H, that is the atmospheric pressure. So what we are going to measure is the atmospheric pressure, that is capital H. The capital H should be in mercury centimeters. Now we are going to assume that the Boyle's law is correct and apply it here. So the Boyle's law is PV equals K. So we are going to apply the Boyle's law to the trapped air. So this is the pressure, this should be the pressure of trapped air, and V should be the volume of the trapped air. We can arrange this equation like this: P equals K over V. Then we are going to write an expression for pressure in terms of these variables. So P is the pressure of the trapped air. That pressure should be the atmospheric pressure, that is capital H, plus the hydrostatic pressure due to this mercury column. So if we consider the hydrostatic pressure, we have to consider the vertical height of the mercury column. So if I draw a triangle, so this is the length of mercury column, and theta should be the inclination. So this vertical height should be x sine theta. So now we know the vertical height. We can write the pressure inside the trapped air as atmospheric pressure plus x sine theta. So this h plus x sine theta is the total pressure inside the trapped air, and this term is in mercury centimeters. Then let's substitute that here. So P is h plus x sine theta. This is in mercury centimeters, but we have to convert this into pascals. So if we need to convert this into pascals, you have to multiply that by the density of mercury and the gravitational acceleration. So you have a term for total pressure inside the trapped air in Pascal. And let's write K. Then we have volume. Volume is the volume of the trapped air. We know that the cross-sectional area, that is the internal cross-sectional area of the Quill tube, is capital A, and the length of the trapped air column is simple L. So the volume of trapped air should be A times L. A times L. Then, if you think about this triangle, we can get a term for sine theta. We will write sine theta as H over capital L. So H is the opposite side of the triangle and L is the hypotenuse. Then I'm going to substitute that term here. So it should be, and rewrite the equation. So sine theta is H over capital L. And that is rho G equals K over AL. So now we have this equation. If I remind you the terms of the equation, capital H, that is atmospheric pressure in mercury centimeters, simple X, length of mercury column, simple H, the length of trapped air column, rho, density of mercury, G, gravitational acceleration, K is just a constant, capital A is cross-sectional area of the Quill tube, that is the internal cross-sectional area, simple L is the length of trapped air column. Then we are going to draw a graph using this equation. So to draw a graph, we need values for x and y coordinates. X is the independent variable and y is the dependent variable. So we can do that by changing the inclination of the Quill tube. So if we change the inclination of the Quill tube, you can see what changes is this simple h value, that is the height to the top end of the Quill tube. So that is the variable that we change. So it should be the independent variable that relates to y. Then you will notice as we change this simple h, the length of trapped air column changes. So this simple L depends on simple h. So simple L relates to the dependent variable. So simple h is the dependent variable and simple L is the dependent variable. So simple h is dependent variable. L relates to the independent variable, that is y. Now I am going to subject this independent variable. But in this case, we are going to consider the reciprocal of the independent variable, that is 1 over L. We do that because we need to get a linear graph. So if you rearrange the equation, 1 over L is equal to these terms. So 1 over L is the dependent variable, that is y, and the simple h is the independent variable, that is x. So if you can see, this equation is in the form of y equals mx plus c. So this is y. This term can be considered as the gradient, that is simple m. This is x plus this term can be considered as the intercept, that is symbol C. So this is in the form of y equals mx plus c. So we gained this equation by assuming that the Boyle's law is correct. According to this, we should get a graph, linear graph, with a positive gradient and a positive intercept. So if the experimental data shows a graph like that, the Boyle's law is verified. So the graph should be something like this. For the y-axis, you have 1 over L. For the x-axis, you have simple h. The graph should be linear, like this, and it should contain positive intercept, and the gradient of the graph should also be positive. From this equation, we can extract the intercept. So this intercept, symbol C, should be this term, that is AH rho G over K. For the gradient, we can consider this as tan alpha as well, and that term should be this, that is AX rho G over K capital L. Then if I divide intercept by gradient and simplify it to the other side, the equation will be capital H capital L divided by symbol X. So the intercept can be gained by this graph, and gradient also can be gained. So we know these two values. Capital L, that is the length of the quill tube. We can take that measurement. And symbol X, that is the length of mercury column, that also can be measured. So we know these two values as well. Only term unknown is capital H, that is the atmospheric pressure in mercury centimeters. So you can simplify and substitute the values and get a value for atmospheric pressure in mercury centimeters. So like that, you can verify the Boyle's law, and also you can find the atmospheric pressure experimentally. So to recap what we just did, I'll explain the experiment step by step in order. So the first step is to attach this quill tube to the stand as shown in the image. So the closed end of the tube should be on the table, and it should also be inclined to the horizontal like this. Then measure the length of the trapped air column and vertical height from table to the top end of the quill tube, symbol H, and note down those values. By changing the inclination of the tube by adjusting the stance, you can get about 6 pairs of readings for H and L. Then you can enter those values in a table like this. So the top row has values for the height measurements in centimeters, and next row values for symbol L, that is the length of trapped air column in centimeters, and this final row contains 1 over L values. So you can calculate 1 over L values and insert them in this last row. Additionally, you need two more read measurements, that is simple X and capital L. Simple X is the length of mercury column, and get the reading from meter ruler and note it down here. And other reading is capital L, that is the length of the quill tube. Note it down as well. So using the values in the table and these two values, we can find the atmospheric pressure, and also those values can be used to verify the Boyle's law. As I explained before, 1 over L is the y variable and this h is x variable. Then you can get this graph. So x term, that is simple h, and y term, that is 1 over L. So using these two rows, you can get 6 coordinates, 6 xy coordinates in order to draw the graph. So if we consider these two values, first two values, that can be somewhere here. And other two values, other two pairs, it should give a coordinate like this. And there should be 6 coordinates. Then what you have to do is to draw the base fitted line. This is like this. Then you can get a value for the intercept from this graph and a value for the gradient from this graph. So the graph you got is linear with a positive intercept and a positive gradient. The Boyle's law is verified, and by dividing the intercept by gradient, you can find the atmospheric pressure as well, as I explained before. Initially, I promise you that I will explain the preparation of a quill tube. So to get a quill tube, you need to have a long glass tube with thin walls. The length of the glass tube should be about 1 millimeters, and the internal diameter of the glass tube should be about 2 millimeters. Now the both ends of the glass tube is open. Then you have to insert a mercury column into the glass tube and keep the mercury column somewhere around middle of the glass tube, like this. So remember that this glass tube is about 1 meter in length, and the mercury column should be about 10 centimeters. This is 100 centimeters. The mercury column is about 10 centimeters. Now the both ends are open, so you have to close one end. To close one end, you need to submit this end to a Bunsen burner. Then this glass gets liquefied and closes this end. And if you remove it, it again solidifies and this end gets sealed off. So you have the quill tube. It is recommended that you have to attach a meter ruler to the quill tube. So end of meter ruler should be attached to the quill tube like this. So you can measure the length variations easily. Okay, that's it for the experiment. And if you have questions regarding the experiment, please comment below.